Hey there, this is Seth Schaefer from Team Just Cause Robotics, and today we're going to be doing a very quick simulations in Fusion 360 tutorial. So here I have a basic part that could be an armor panel or what have you. I have a bunch of holes for, say, 1/4-20 screws spaced out. So this is a 6" by 2" by 1/2" piece of aluminum, 6061 right now. And I'm going to show in simulation difference between this very basic part, a more optimized shape, and then a slightly better lightweighted part with some pockets. So to start out with, let's switch to the simulation tab. So here, normally when you come up to it, you'll get this page, which shows which type of thing you want. For now, we're going to use static stress because that is what we're going to care about when we're talking about loading on a panel that can be easily simulated. Ideally, you would use impacts in a lot of cases for combat bots, but unfortunately, that is very complicated to set up properly and usually requires some extra features. Like, I have no idea how it's even in preview right now. I don't think they actually have a final release of it currently for Fusion. In SolidWorks, I don't even think that my $3,000 CAD package that I get for work has the ability to do impact simulations. So really, you're gonna wanna start with static and just use high loads to get a general sense of where the weak points of the part are and where there's weight that could be removed. So start out with study materials. Right now it's set to 6061. You could change this based on whatever you want. Same as model is what we want here, and then the yield strength is part of the material because it's not a custom material, it's like part of the Fusion material library. I'm just going to delete static study 1 because I didn't do anything on it. So now we need to apply constraints and loads. So for our constraints here, let's assume this and this are bolted to the frame. So I'm going to set those both as fixed, the inside of those bolt holes. And then let's say that we also want to put a load, or well, actually, let's do a rigid constraint on all of the bolt holes. Fixed constraint on all the bolt holes. And then let's say this panel is like a side panel or whatever, and there's going to be a load right in the middle here. So we get structural loads. Normally when you click on a face, it's going to distribute the load across the entire face, but that's not really realistic. So what we're going to do instead is select angle and then limit target. And this actually allows us to select a zone in which the force will act, as opposed to selecting the entire face. So I'm going to set it to act in, say, a 0.25". I think that is actually a radius, not a diameter, judging by the fact that my part is 1/2 inch thick. So it's going to be in a 1/2 inch diameter, basically. And let's call this 100 pounds. Okay, so now we have constraints, we have a load, now we need a mesh. So in mesh settings, generally, smaller is better. If your part's really complicated, you might need to pull this up, but essentially, the rule of thumb that I've been told is you want to make sure, when you make the mesh visible, and to actually compute it, that you have at least about 3 boxes width on like your thin sections. So in this case, like one of these wall thicknesses, we want at least 3 boxes. And here you can see we have way more than 3. We have 1, 2, 3, 4, 5, 6, 7, 8. So that should be a plenty fine mesh for what we're doing here. So now you can see here in pre-check, the setup has all the information required, so we can get the results that we need. So to click on results, and it'll ask to compute. We click yes. And now everything is going to be in the cloud. I have the education version of this, so everything is free for me. I believe that it's going to possibly require you to use cloud credits for the hobby versions, but I think you get some for free. If you have a university email, even if you already have like a hobby license, you can just create a new account with a university email, or even possibly a normal email. I don't think they even care if it's a .edu, and get the education version, which gives you infinite free cloud credits for doing renders or performing simulations. and it unlocks like 90% of the functionality of the paid version of the platform. So just wait a couple minutes for this to happen. Okay, so I've just got my simulation completed and received the results. Now let's take a look at what we've got. So the first thing that comes up is what looks like a very horribly bent piece of metal, and that is because it is creating an extremely exaggerated deformation. So if we actually look at the actual deformation, this is what it looks like. So it is very, very slightly bowed, but not much. Go back to adjusted, so you can see the exaggerated deformation. And these numbers here are factors of safety. So you can see here we're on safety factor, and everything is blue, which basically means that the minimum for blue zone here, down here, is 6. So everything is higher than 6 safety factor. This is not a very helpful plot. Let's look at the stress plot. This is what most people think of when they think of doing a static simulation, which is an actual like stress distribution plot. You can see here the minimum safety factor that it calculated is 13.69, which basically means that 100-pound load is absolutely minuscule compared to what this panel can actually handle. But that's fine because this stress plot will look the same regardless of how much load we put on it, since the scale will just adjust to whatever it is. The important things here is to show where the stress is concentrated. So there are two ways to do that. Number one, you can just look at it and see what areas are red and yellow and green and whatnot. Number two, more helpfully, is we drag these sliders. We can actually zero in on the areas of the highest stress. So as we decrease this, you'll see that the load tends to be carried on, unsurprisingly, places in between where the different connections are. So if I switch this back to actual just so that we can see it in a straight line, you can see that the load tends to be carried along this bottom edge and these faces. The reason this is important to note is that it's pretty much always the case that loads are carried around the outermost extents of a piece of material. And you can see here also, because the load is down low, this bolt hole isn't doing nearly as much as these two to actually carry the load. So what does this tell us? Well, first of all, as we move this down, you can see this whole corner is basically doing nothing. So that tells us that's material that we could very easily remove and have the part be just as strong. And then also, interestingly, something that wouldn't be quite as obvious maybe is that this area here appears to be taking none of the load. However, in an actual combat scenario, let's say it could be hit anywhere along this line or even like up here. Maybe we can afford to get rid of material in this region around here, but not necessarily want to take it out here just in case the load were over here somewhere. So let's see what this does for us. So we have a safety factor of 13.69 right now, and the part weighs 9.23 ounces. So if I now just decide to take a slice out of here arbitrarily, now we have the part weighing 7.72 ounces. Let's do even more than that, actually. So now it is 7 ounces instead of 9.2 ounces. And if we go back into simulation, we can simply click results again. Whoops, that's not what we want. We want to remesh, because the mesh is what's actually basically having all the calculations happen to it, not the model itself. So once we recalculate the mesh, we will see the mesh generated correctly, and now we can get new results by actually running the study again. Solve, that's the one. Okay, now we can actually get the results. All right, so now we have our new results here. So first things first, our actual safety factor decreased by almost nothing. So basically the strength to weight of this part is now dramatically higher because it went from being about 13 safety factor at 9.23 ounces to about 13 safety factor at only 7 ounces. And you can see here, if we look at the stress plot again, once again we have basically the same pattern, though obviously now it hits this top edge here instead of where it used to be all the way up there. But the concentration of the stresses is still highest at the bolt holes, so it's never going to be like that much weaker from removing material that isn't directly around the bolt holes. So let's see what else we could do to lightweight this part. Well, what about pocketing? So if I just project the whole thing and then offset, that's one way that I like to do this, is I'll say like I want a minimum wall thickness of say 0.25, and then I want to have material around all of the bolt holes. So I'm going to set all of these equal to each other, and then say I want a minimum of 1 inch of material. The general rule of thumb that I've learned from a engineer who worked on the F-22 aircraft is you want to have at least 1.5 hole diameters of material around your hole. So here we have a 0.135 inch radius or a 0.27 inch. So 0.27 times 1.5, whoops, around the hole, plus 0.27. So this would be like the minimum amount of material around the holes basically that you want. In other words, this distance from center to the edge here is 375 right now. We would want the distance from, say, like this point to the wall to be at least like 0.27 essentially. So right now it's actually a little close, but for this purpose it's fine. So I'm just gonna say I want 0.75 around each, and then now I have all of this material that I could in theory remove, or not remove, but start to pocket out. So let's try that. Let's pocket out minus 0.25, and then because I would be milling this part to do those pockets, I'm going to add a bunch of large fillets because a tool radius needs to get into any sharp internal corners. So let's say 1 inch, or okay, that's a lot, 0.5, maybe even just 0.25, because I'd probably use a 1/2 inch end mill for this, 0.3, just to give it a little bit more clearance there. And then this looks a little bit drastic, so maybe I'll come back in here and add some diagonals to strengthen it a bit. This is all purely arbitrary, by the way. I have not thought this through at all or prepared this ahead of time. Whoops. And let's make that, say, a 1/2 inch, maybe 3/8, looks a bit thick. And I'll try and have it somewhere like more or less split this into like 2 roughly equal area zones. Up to here, and then again I have to fill it out. These 0.3. Okay, that looks kind of ridiculous. That fillet's a bit big. Let's make it like 0.15. That's a little better. Okay, so now we go back in the simulation, generate mesh. Oh, I forgot to check how much this part weighs. So now we're down to 5.37 ounces. And let's see, pre-check, we are missing the load because I kind of killed the face where that load was applied. So let's fix that. Loads here, angle, and then dot to drag. Oh, there we go, limit target. I forgot to click limit target. I'll put that roughly in the same spot. Maybe like here. And then 100 pounds force. Whoops, I forgot to set the diameter to 0.25 to make it the same. Okay. And now invalid load force 1. Interesting. Probably because it's clipping. Is that good? No? Oh, this is the one from before. It's just not registering anymore. Okay, there we go. So now we can hit solve. Oh, whoops, we have to recalculate the mesh again. Don't we? Oh, just kidding. All right, so now we can just click solve and solve it again and see what we get. All right, so we have our results back. Our minimum safety factor is down to 8.97, which is still plenty adequate for something like this. And now we're seeing much of the load is, or much of the stress is more concentrated in this bottom area here in the bottom left. So we can see now the load is definitely following the little rib that we added here. So that means that was in fact useful to some extent, but still all the concentrations are at edges and corners, which is to be expected. Here I'm seeing a lot of yellow, so maybe I would want to add a bit more material out here to lessen that, but still it's highest right at the bolt holes, unsurprisingly. So yeah, that's just a really quick overview of how you can use the fusion simulations to help guide your designs and save some weight in them without like completely wrecking the design. Thanks for watching. Don't forget to like and subscribe for more content. Also, check out the Just Cause store in the description if you'd like to support me with making these videos.